And I will try to record the lectures, but no guarantee, and like put them on YouTube. But no guarantee that that will actually work, so try to come to class. All right, so welcome again to System Software. Hopefully you're in the right place. This is a huge class. It's like 250 students with a wait list. So let me go over the class and go over the assignment and everything. You can see if you're still interested in taking this course. I know it's required. But let's start off with a simple question. Why bother studying system software, and specifically in this course, compilers, because we're going to focus a lot on compilers. Why bother studying it? Anyone care to wager a guess or a thought? What's that? It's important? Okay, I think it's important, but do you? Why? Why is it important? To optimize what? Okay, yeah, so you can optimize code. Why can you optimize code if you know about compilers and system software?
Well, if you get into, I guess, machine code, depending on like how you write the code, certain ways may be inefficient in terms of how it's read in, I guess.
Sure, yeah, if you understand your tooling, you can be a more efficient developer. Yeah.
System software gives you a better understanding of like working with higher level architecture versus like more low level programming that we've been doing.
So it gives you understanding of your programming environment, is what you're saying?
Yeah.
Gives you, more than just the bare hardware, it lets you actually use it efficiently. Is that kind of more or less? Okay, what about you?
More to learn about the software inside and out, and especially the bigger the program is, those little poorly optimized things can add up, and it can run very poorly on certain machines and not work as efficient.
Sure, the point is that for small programs, like you write in class normally, efficiency doesn't really matter, knowing your tools doesn't really matter, and those little inefficiencies can build up as you get a larger piece of software. Yeah?
So someone knows how compile works.
So some people, if you're really interested in this course, you can actually do compiler development. You don't need a lot of people for that. It's kind of slow moving because if you change the compiler, then all the developers get annoyed. But yeah, for people who are actually interested, and so I do research in using compiler techniques. So if you have any interest at all in the research that I do, maybe I should actually give a little ad for my research lab. But I also do research in this area. And so if you really find this interesting, you find the programming project interesting, reach out to me. And there are opportunities to learn the ropes in research and see if you want to go to grad school, perhaps. But I'm guessing for most of you, you're looking for a job, make money, right? And you have some interest in computing. And so there are good practical reasons for this class. So one, as some people hinted at, is to know your tooling. So this is a page from Isaac Newton's notebook. So hopefully you all learned about the Enlightenment physics and how Newton kind of came up with these very accurate at the time models of gravitation. But what you might not know is that in his studies of optics and light, he ground his own lenses. He developed his own tooling in order to do the research. And so think of system software and compilers as learning how your tools work so that you can better use them. And you can even build them yourself if you need to. For instance, carpenters also often build their own tools. So that's one good reason, one practical reason, especially if you're going into development or anything in computing, is to just know the internals of your tools. It's easy enough to treat them as a black box and just use the language, but as some of your colleagues said, that if you understand how the tool works, you can better use it. You can make code more efficient if you know what's going to be faster or slower in a certain language. And in the same vein, understanding these tools will help you be a better programmer. So it's a little hard to read, but this is the IEEE Spectrum's top programming language. They have some metric for determining what are the top programming languages. At the top here, I know it's a little hard to read, is Python, kind of surprisingly. I didn't think about these results until I looked at them now. This is from last year. Java, C++, C, which is sort of like a dead language that doesn't know it's dead. It re-emerged several years ago because of the popularity of embedded computing. We have JavaScript, C#, SQL. And so you might be thinking, oh, I have to pick the right language to learn to go into industry, and then 5 years later, when you're looking for jobs, or 4 years later, well, a different language is the hot language. But if you learn about how programming language tools work in general, it's going to make it much easier to learn new languages. Because most of these languages use the same principles. They have the same kind of constructs. They use the same kind of compiler and interpreter techniques. And so instead of trying to focus on one language, by learning about system tools and compilers in general, you can learn about all computing languages, more or less. Okay, so there's my second reason. My third reason is just, it's fun, it's interesting. And I know this is school for you. You sort of feel compelled to do this, and you may or may not be as interested as I am. But it is, to me, genuinely interesting to see how these tools work, particularly compilers, because they are both the discrete side of computer science, but also the physical machine side of computing. It's the merger between the two. It's taking this abstract thought that you can't put discrete equations into a computer, you can't even put C into a computer and have it run. The compiler is what connects that abstract math world of computing with the physical, real world of actual machines. So a little about me. My name is Paul Gazzillo. I'm an assistant professor here. I do research in programming languages and software engineering and security. And I use a lot of these techniques that come from the compiler world, because it was my favorite class when I was in grad school. And I use them to try to solve problems in security, try to find the bugs, security weaknesses, try to automatically analyze software. And so I guess maybe I can give a little ad for my research lab. If you go to my webpage, I've got a little tab here on research, and you can see the current projects that I'm working on. These software configurations and analyzing configurable software, these are the ones that are most relevant to compilers and programming languages. And there's even papers here that if you're really inclined, you can go take a look at. And if you have any questions or any interest in research, let me know. Okay, so let me give a quick overview of what a compiler looks like at like the 10,000-foot view, and why this is so hard to reason about compilers and think about them. Okay, so I think you've all used a compiler before. For instance, well, let me make this concrete. So you've all used, say, GCC. And how do you use GCC? Well, you take your input program, which might be something like file.c. You pass it to your compiler. Sorry, new tooling I'm using. You pass it to your compiler, and what do you get as the output when you pass your C program to your compiler? What's that? A.out by default. What is A.out? It's executable. It's machine code in the format that your operating system uses to know how to load this machine code and actually start inputting it into the physical processor. So you get this maybe executable file or object file. So that's the 10,000-foot view of how a compiler works. Now for the compiler developer, what they need to do is they need to write a program, because a compiler is also a program. And that program has some source code. So this might be like compiler.c. But if you're writing a compiler in C, well, what do you have to do in order to run a C program? You have to compile it. So we still need some compiler here. GCC or something like that, whatever compiler you're using, in order to generate the actual compiler binary. Let's just call this a compiler now. So we need our compiler executable. If we're writing a compiler in C, for instance, we need the compiler executable in order to actually build the compiler to be runnable. Anyone see a challenge here with doing that? Yeah, it's like a loop. It's like a circular definition. In order to make my compiler, I need a compiler in order to compile my compiler. So this is to me what the crux of compiler writing is, what makes it really hard. So this is called the bootstrapping problem, and it happens in operating systems as well. It's where the term boot comes from, booting your machine. You need some initial program in order to run your operating system, run whatever code you want to run. And so the challenge is you can't write compiler and compile a language until you have a compiler. So the solution to this is to write the compiler in machine code first. But we're not going to do that. We're going to assume we have a compiler. But what makes this really hard is that normally we're thinking about writing a program like this. We're writing a program like file.c. And you have some input in mind. Say you're writing some sorting algorithm. So we've got some array that you're inputting for instance. And you pass that to your executable, not to your source program. You pass it to your executable, and you get some output. Some sorted array output. That's bad alignment. So normally when you're writing your C program, you're thinking about the input and output that that program has. Well, for a compiler, what's the input and output of a compiler? What's the input of a compiler? Source code. It's the program. This is the compiler executable. And you're not writing something that's going to run this program. You're writing a program, this compiler program, that's going to take in another program in a different language. And what's the output of the compiler? An executable. It's another program. So compiler takes some program in some source language like C and produces another program in a different language. So we can kind of like have a loose definition of what a compiler does here. And a compiler is really just a translator. This compiler is not executing this program. It's not interpreting it. It's not trying to find the answer for this program. What it's trying to do is take this program written in one language, in this case C, and just translate it into another language, in this case assembly. And usually when people talk about compilers, they're talking about going from a high-level language to a low-level language. That is a language that's closer to machine code, what the actual machine processes. And so the tricky part about writing this compiler is we're writing the source code of the compiler, and that's going to be in some language. In this class, it's going to be C. And we have to take as input a different programming language. We're going to use a simplified version of C called Simple C. And you have to generate code in the output language in assembly. And so when you're trying to write your compiler, you have to think about 3 different languages and 3 different programs at the same time. You think about the program you're writing and how that works. You have to think about the input program and know the meaning of that program in order to translate it. And you have to think about the output program language, machine code. Kind of make sense? So in this class, we're going to learn how to do that. But to me, I think this is the hardest part of writing a compiler. It's the most sort of mind-bending part of it. It's very meta. You have to think about multiple languages at the same time. And the sort of main pitfall that I think people fall into is to think about what the answer of this program is, what the output of this program is, when really you should be thinking about how do you translate this program so that it runs for all possible inputs that it can take. So in contrast, an interpreter is very similar. It gives you a way to process a language. So if we've got an interpreter here, let's say it's like the Python program. You have your input program, say file.py. An interpreter, in contrast, takes the program source code and some input. Let's say this is a sorting program. And it gives you the output. So at least at a high level, there's no translation step, although in practice, interpreters really do some compilation first. But the difference here is that as the interpreter developer, your goal is to figure out how to get the output for one particular input of the program. Whereas with a compiler, this compiler program needs to reason about every possible input to the program and make sure that every possible input that the original program can take matches the input that the output program could take, and that they have the exact same outputs. They're equivalent programs. Celebrate, I guess. All right, so I think I've belabored that enough. Questions at all? Questions? Yeah.
So for interpreters, learning is only looking for a specific output of the
Yeah, exactly. That's all the interpreter needs to do. The interpreter only needs to figure out one output for one input of the program. In reality, these two techniques are much more closely related than you might think. So for instance, in Java is sort of a combination of the two. So in Java, you've got the compiler, Java C, takes in some program, converts it to bytecode. So this would be like file.class. And then this class file is not in any hardware machine code. It's written in Java bytecode, which is interpreted by the JVM, the Java Virtual Machine. And it's the Java Virtual Machine that takes the input and interprets the program for one particular input. So yeah, I guess loosely you could think of the interpreter as giving you one input of a program and output, and the compiler as figuring out how to give you all inputs and outputs in a different language. All right, good question. Questions? Other questions? Okay, so let me go over the kind of mechanics of the course using the syllabus. So let's take a look here. Oops, probably shouldn't have done it that way. Okay, so you can see all the kind of required information here. You need these prerequisites. We're in section 2. This is my web page and email address. This is the TA. So tentatively, I've made the office hours these times. I was planning on going on web courses and actually like taking a poll because it's very hard to coordinate 251 people's schedules. Who do these times work for? Wow, okay, so who do these times definitely not work for? For whom does Monday not work for? For whom does Wednesday not work for? Because you have like a class that's Monday, Wednesday, I guess. All right, so I'll figure out some. I'll improve these times. I'll put some polling on web courses. Hopefully, I don't think we'll need office hours for the first week, maybe hopefully the first 2 weeks. But there are ways to contact the instruction team that I'll go over as well. Okay, so I think you hopefully know this. This is the course schedule. This is like a double lecture every Friday morning. And while I have you, let me take a little poll on how we should run this double lecture. So in the past, some students wanted to just go through, 2-3 hours in one shot. Probably we're here physically, so that was on a virtual course, so maybe we need a break. So who would like a break between the two lectures? Who is radically against a break between the two lectures? Not many, okay. So we'll have some sort of break. Who thinks 10 minutes is a good break? Who thinks 15 is a better break? Who thinks 5 is a good break? I think 10 wins. So it doesn't have to be so precise. We can do it on demand. And I've sort of organized the lecture so that it's like an hour of content, and then it'll be, give or take questions. There'll be 2 of those chunks. So if we get out early, who would want to get out early? Who is radically against getting out early? Okay, some people. But we'll get through the content. I think we have plenty of time. It's like almost 3 hours, but I don't think we'll need all the 3 hours. All right, so let me take some notes to record your answers. So 10-minute break, 1 out. Need to have different office hours, Monday or Wednesday. And okay, so I'll figure out. I'll figure that out later. So it's been it's been less than an hour. I think we can get through this and take a break in 20 minutes or so. All right, the final exam schedule is up. If you look online, it's from like 7 a.m. to 9:50. That seems like insanely early. So we don't need the exam to be 3 hours or 2 hours, whatever it is. So I have the exam at 8:30 to give you guys enough time, about an hour. And we'll talk more about the exam later. It'll just be based on the homework questions. These are the lab sections. In the past, I think there's been no problem with like picking whatever one you can attend. It'll be the same lab each time. I guess try to stick to your own lab because the class the classroom may not be able to support it. But I think in principle, there's no issue with picking whichever lab you can make. But yeah, I guess try to go to your own. Okay, here's the course schedule. In this first chunk here, it's going to be largely introductory material. And I have a couple of projects that are easy. They're just like hand copying a very, very simple compiler for a calculator. This is probably the only time in this class and probably the only time ever that you can just like hand copy code. But the assignment is not to do the compiler. The assignment is to give some muscle memory for these compiler tools that we're going to be using and to make sure that your programming environment is set up. And I'll go over those assignments in a couple weeks when I actually go over that toy compiler. So this first section here, the first 4 weeks, is introductory material. We'll go over the actual programming environment we're going to use. I'm a big fan of using the command line, the Unix style command line, and so I'm going to impose on everyone to use that same style. I think if you learn the command line, it's much easier to use the easier tools, the graphical tools that you have. But going the other way is very difficult, and there's a lot more things you can do on the command line. You get a lot of power in using the command line. But I'll go through next week all of the tooling that you'll need, all the commands that you'll need, and all the instructions for the project will also have all the commands like exactly that you need to run. And if you have any questions, there's a discussion board that you can ask questions or come to office hours. But I really encourage everyone to use the command line and to standardize it. We'll be using a virtual machine that will take a little bit to install. But we'll go over that later today. Okay, the second part is the front end of the compiler. This is the compiler that processes the input language, turns it into a syntax tree. We'll talk a little bit about that as we talk about the intro to compilers. But it's the front end, the language processing part, the input language processing part of the compiler. And there's a lot of kind of discrete math here, regular expressions, automata, push-down automata, finite state automata. I think discrete is required for this course, is that right? Not discrete 2, discrete 1, okay. So you probably learned about regular expressions or automata, I think? No? That's discrete 2, okay, so you did learn about that. We're not gonna go in, it's not gonna be like discrete 2, but I think even if you don't understand the math behind it, regular expressions are pretty straightforward. They're a common programming tool. So that's the front end for the second 4 weeks. And then the next 4 weeks are the back end. This is the part of the compiler that generates the machine code. And we'll see how you generate machine code for all of the common features that you see in programming languages, arrays. We'll do pointers, which are, I know, always a point of confusion when people are learning C and low-level languages. We'll learn how they're actually implemented, and that might actually help you understand how to use them better. You know, one reason why knowing your tools is useful. And then we'll do some special topic. I have a captive audience, so I'll probably show some of my research. We'll do exam review, and then have the final. Questions about the schedule? Yeah. Labs will go over basically whatever questions you have. So it'll go over homework, it'll go over projects, basically whatever's due that week. They'll go over the course material from that day and basically answer questions for you about the homework. Yeah?
Wait, so is labs, like, because it's kind of like a catch-up, will it be required?
I mean, I can't say it's not required. I think it's on the schedule, it's on your schedule, part of your credit hours. I guess I mean, you're all adults. I'll leave it up to you. I think most of you are adults. I'll leave it up to you. So, you know, how you wanna use the labs, but they're a resource for you to use. Other questions? Yeah.
Will there be a lab today?
No, there's no lab today. I think I sent it in an announcement on web courses. There's no lab today. Other questions? Yeah.
Do you have to have a virtual time, or are they all in?
No, it's all physical. I think you see, well, some classes are still virtual. This class is in person. I am recording the lecture, you know, everything that's on the screen and my audio, hopefully. There's really no guarantee that it'll work. I try to do it correctly. I'm using different tooling. I'm using OBS to do this time. So as long as that works, I'll try to post these lectures. But no guarantee that it'll actually work, because it's not a virtual course, it's in person. But I try to actually record it because I know it's helpful for students to see the material, or if you miss a class or something. Other questions? Okay, so that's the exam schedule. Now this is the information about the labs. We went over that. So here is the set of assignments. So you can see here I put the project due dates for everything. The toy compilers are very easy. It's just literally hand copying pictures of code and just getting your environment set up, getting it to run and compile. And then you have a couple weeks after the end of each section, after the end of the material that describes the project. So the project one is the front end. So it's, you know, once you have these first two classes, you should have enough to do the first project. Project two, you know, basically you have a couple of weeks after the material is described in order to turn in that part of the project. There's an assignment right now in web courses for academic activity. It has to be due tonight. This is like the UCF rules. And if you have like financial aid, you like have to show your academic activity. It's literally just putting your GitHub username. If you don't have one yet, you can just put what you think it's going to be. But it's very easy. You just literally do the assignment, and especially if you're on financial aid, you like have to do this academic activity to show that you're in the course. So that's easy. You just literally put your GitHub username. Who does not have a GitHub username? Okay, who does? Everyone does. Oh wow. Okay, GitHub is, yeah. So Git is not GitHub. GitHub is a centralized repository for holding Git repositories, but you don't need GitHub to use Git. But I use the GitHub Classrooms functionality. So if you don't have GitHub, are you opposed to using it, or you just don't have it? Okay, so you can sign up or put the name that you think it's going to be. We're going to do all of our grading on GitHub. You can talk to me if you have any issues about using GitHub. In the past, I haven't seen any issues with it. So that's like due tonight for the academic activity requirement, but it's very easy. Okay, so the kind of real part of the grade is homework assignments. There'll be 12 homework assignments for each week of the compiler description starting today. It'll be due the following Thursday, the next Thursday before the next lecture. So you have like 6 days, 6.5 days to do it. So it's always going to be a week except for like spring break. It'll always be the following week that you turn in that homework. And this will be on web courses. The due date will be there in the information. So here's some examples. Today's lecture, It's going to be due next Thursday night. So basically the day before the next lecture. And in this case, this is the spring break, so it's due 2 weeks later. So grading, we're not going to grade super strictly for correctness. It's really just for you. So as I think we'll go over in the slides, in prior course feedback, some students actually said, could you give some like competency questions or some questions at the end of the lecture to help keep people on track? That's really more what it's for. It's not meant to, be a lot of busy work. The hard work comes into doing the compilers. So the first one is these toy compilers that I described. There's 2 of them to write. The whole repository is given to you with some files as images that are images of source code. And then all you have to do is handwrite that source code and make sure that your project compiles and runs. That's it. So I was, you'll hear the late policy in a second. I don't have a late policy for this because I figure it's pretty straightforward. But if you have any issue or any problems turning this in, you can let me know. And then here's the bulk of your grade, almost half the grade, is the compiler itself. So there are 4 of these projects. We grade them automatically. We'll provide you a test suite where we have public and private parts of the test suite. And so you'll be able to basically see your expected grade yourself. But as we'll see when we talk about testing, pretty much no test suite, particularly for compilers, is complete. It's not going to give you every possible input. The inputs are infinite, technically, for compilers. So you should definitely be writing your own test cases as you go. But these test cases we have are for grading purposes. So if you can get all 4 pieces together and all running, you'll get a little bonus for doing that. It's nice to see everything work together, but it's also really hard to do. So each project can be done in isolation. So the compiler, you need all the phases to have a complete compiler, but if you get something wrong or can't get something right in one phase, that could affect the correctness of the other phases. So each project, I'll give you the solved version of it in binary form so that you can just work on that part of the compiler in isolation. That kind of makes sense? You'll see when we get there. Then there's a final exam. This will be based on content from the lectures, homework, and projects. You can bring lecture notes, although I guess no electronic devices, unless you have, if you need student-assistive services. You can also, I'm sure you set that up yourself. That you'll be able to use digital, be able to do it digitally. And then a kind of 2% loosey-goosey participation grade. Okay, late policies. So all homework and projects are considered late after their due date. Homework assignments you can turn in a week late and get half off. They're only 2% each. So you can get half off for those. The toy compilers, as I said, I don't have a late policy for this because they're just like literally hand copying code. But talk to me if you object or you have any issues doing that. Now the projects, because this is the bulk of your grade, and it is really hard to do, this compiler project is not going to be easy. It's in C. It's a full compiler going from a restricted version of C to Intel assembly. Not an easy project. But I want everyone to try to get as much as they can. And so technically it's late after the due date, but you only get a very small penalty for turning it in late. So technically you can turn in any piece of the compiler project up to basically the last day of class, like the day before the final. And you can retry as much as you want. So if you turn it in on time and you only get like 50% of the grade, you can turn it in again. As much as you need to turn in. Because I want you all to get this experience of actually building this compiler. It's probably going to be one of the biggest things you build in class, or at least up to this point. It's probably, yeah.
So if you turn it in on time, and then we want to retry it again, and submit it again after it's late, does the penalty apply to that?
Yeah, the penalty applies. So it's a little bit of a trade-off between like, am I really going to get that extra, 3 or 4 points, or is it worth it? But I recommend trying, getting it all working. You do get this extra bonus for complete compiler. Maybe I should make that bonus higher so it's more of an incentive. But you get a little bonus if you have a complete compiler that works. But I try to make this where it's like kind of a token penalty for doing it. Yeah. No. It's, yeah, just for each project. So you could lose a total of eight points. So I guess that, if you want to get you can work out the math if you're like trying shooting for an A, or there's some sort of, I guess, like gaming to do here. But my goal with this is to have you try to get each phase. I wouldn't wait till the end of the semester because some of these assignments can be pretty brutal. They can be pretty tough. So, the goal of this is to try to incentivize you to turn it in on time, do your best, but not to feel so disheartened that you've not gotten it complete, because you can still try again and you can still come to office hours and improve it. Got to make sense? Because I really want you all to get through this assignment. It's a good experience to build this large piece of software for reasons beyond just understanding compilers. If you're going into software development, you're almost certainly going to be working on projects that have already been written. It's more common to do maintenance and development than it is to build projects from scratch. I mean, with exceptions. If you're working for a startup or you work on a new project. But you're mostly going to be working on already large pieces of code, trying to do debugging, trying to use techniques that'll, as one of your colleagues mentioned, techniques that make it easier to have faster code. That's when it gets large. And so I really want you guys to have that experience of doing some real-world development, using real-world version control tools, and actually getting this successfully done, because it is a hard project. I will not, blow any smoke about that. It's a hard project. Okay, questions? Okay, so this is the late policy, meant to encourage you to keep trying to get that project working. This is the letter grades. There's pluses, no minuses. Let me know if you have, I've used this for years, this grading scheme. If you have any issues and concerns about that, let me know. And then here's a description of what the course outcome is. We're going over that now. There are no required course materials. And in the past, I've given readings for the recommended ones. But I think the lecture notes should have all the information you need in order to do the project. But if you have an interest in compilers or further developing your programming skill, these are a couple of really good books. This is kind of the theoretical book, the so-called dragon book, if you've ever heard of it, because it's got a dragon on the front of it. This is the dragon book. It's kind of like a lot of discrete math. This book I also highly recommend, The Practice of Programming. This is not a compiler's book. This is a book about doing development, and it's C-based. Goes over testing, regression testing, and just good practice when doing programming. And then if you're really interested in compilers, these are all really classic, good compilers and programming languages books. So questions on that? Questions on course materials? So lecture notes should provide sufficient information. I think it has it in the past. But yeah, if you're interested and you want to spend the money on books, or I think some of these you can get pretty cheap online, especially the Dragon book. It's been in use for years. So read these policy statements. These are the core policy statements. All the projects are individual. There's no group work. Plagiarism or cheating. Don't do that. You may not get caught, but you might get caught. In the past, we have caught cheaters, particularly the graders and TAs, who are also students, I think are a lot more aggressive than I am about it. So you might get found, and I have had to fail people, unfortunately, because of cheating. So take a look. Yeah, take a look at all of these. I think you've probably seen this a lot before in other courses, but take a look. Okay, questions about the syllabus? Yeah.
When you mentioned the test suite, are we going to have access to that?
Yeah.
So we would know
Yeah.
if we passed that project.
Yeah, so I mean, we're going to hold out some private tests. Like we'll have a public version that'll the test, and then we'll have a private version.
And will the private version is what you're going to use to grade it, right?
No, we'll use both to grade it. So you'll have a good sense of what your grade is going to be.
And will they be like the same level of difficulty? Or will
Yeah, they'll be similar. Because I guess just to make sure that because you could if you just have a test suite, it's very easy to cheat. You could just write. It's like teaching to the test. You could write the compiler just so it passes tests. But we'll go through how to do the development, but it's really hard in compilation because there's so many possible inputs. You know, it's like, I want to compile x plus y versus x minus y. You might get x plus y correct, but x minus y might be broken for some, you know, little annoying reason, some annoying bug. So it's got to be like equivalently difficult tests. It's just sort of to cover more of the input language is basically what it's designed to do. So if you're using the practices that I'm going to go over today to do your development, which I encourage you to do in all of your development, basically making little tests as you go along, making sure you're covering all of your inputs, you shouldn't have an issue. And that test sheet will kind of give you a sense of whether you've hit all of the things you need for grading. But don't just rely on the test suite. This is a classic mistake in development. Yeah?
Are we going to be using Canvas or GitHub to submit this?
Oh, yeah, that's a good question. So, and yeah, I did not, yeah, I covered that in my slides, but it's a little split. So you'll see on web courses so basically for homework is submitted on web, so let me do it this way. So homework assignments and this like logistics, that's on web courses. And all of the programming projects are on GitHub. So it'll be in web courses. Web courses will tell you in the assignment, submit here. And there won't be a submission. It'll tell you, go to this GitHub Classrooms. So does that make sense? So I hope that's not too annoying, but it's, yeah, using GitHub, I want you guys to have experience using version control. And GitHub Classrooms is a very easy way to do that. So if it's a programming project, it's going to be on GitHub. If it's like an academic written assignment, it'll be on web courses. But yeah, good question. And the final, I plan to have it in person on paper. That's my current plan. Yeah?
Is it cumulative?
The final? Yeah, so there's only one exam. So I guess that's both cumulative and not cumulative. There's only one exam. So it'll be from the whole class. Other questions on the syllabus? Yeah? I'm sorry. Say it. When will the homework be released? I'll release it the day of the lecture. So I will try to do it actually the night. I'll try to do it before the lecture. I should also point out that for all of these slides that I have are here in like HTML page form with my notes. And I will try to release these before the lecture. So you'll see the notes and the homework in web courses will be released before the lecture. So you'll have a little less than a week to do them. But yeah, I'll release them. And if I don't do that, then and I forget or something, then I guess you won't have that homework, but it'll be due later. But I will, try to make sure on schedule before the lecture every week, probably the night before. Lecture notes will be up. Homework will be up for that week. Videos, so videos are sort of unofficial. They're not really part of the course. I'll try to get those up sometime after the lecture. Let me make sure it's actually still recording. So I've had in the past where like my lecture recording has gone wrong somehow or audio wasn't there. So I wouldn't depend on it, but I will strive to make sure that all the lectures are recorded and they're up, I don't know, within a week after the lecture. I'll try to do that, but it is an unofficial part of the course. Other questions on the syllabus or mechanics of the course? Yeah?
Are we using uses for this course?
No. So that is a good question. Yeah, we'll cover that when we get to the virtual machine. I'm assuming that you all have hardware that you can run a virtual machine on, but you may not. So if you don't, you can let me know. I can set up Eustace access as well, or set up something, get something for you. You can tell me personally if you have any issue with that. But I'm assuming most students have like a laptop or something they can run on. But if you don't, let me know. I don't think I've had anyone yet in the past, but there is school hardware that you could use as well. All right, other questions? All right, so let's see. Let me finish up the mechanics of the course, and then, let me finish up the mechanics of the course. So, in the last overview of this course, I haven't taught this for like over 3 years. There was a request for more in-class coding and demos, so I added that the last time I offered this course. I changed it so that you don't have to handwrite the lecture and parser. Instead, you use these tools that generate them automatically. And I kind of spaced out the course in a better way. The last version of this course went pretty well. There were a couple of comments. So one was staying on topic, not going off on tangents as much, which I do have a tendency to do. So I'll try to like leave any long questions. So my plan is to actually leave a chunk of time at the end of the lectures for open questions, and then you can take an extended break, or if you don't have any questions. And I'll try to keep the lectures more on track, avoid tangents, which I'm a professor, I talk for half my life, so I guess I like to talk. So I'll try to avoid going off on tangents, try to stay with the material. And the other one was competency questions for each lecture. So there's actually students asking for questions. I think in the past I had very little homework, and I hate having homework penalizing you because it's almost measuring your ability to be punctual rather than like do the homework. But it is useful, and it also is good preparation for the final. So for this offering, every lecture there'll be a homework, but it'll be graded mostly for effort. If you turn in something blank, we're not going to give you the grade. But if you try and take some time to do it, then you'll get the points. So that's changes from the last offering. So I went over this a little bit. So web courses is where you'll turn in assignments. Turn in homework assignments. There'll also be an assignment for each of the projects, but it'll instruct you to turn it in on web courses. I've gone over the course webpage. Lecture notes will be available there on the day of the lecture. And new this semester, I'm using this site called Ed Discussions. Has anyone used this before? Wow, okay. So I hadn't used it before either. Another faculty member, I guess, gave me an invite and told me about it. I used to use Piazza, but they kind of changed their business model, so I stopped using that years ago. Ed Discussions, you've used Piazza, right? Everyone has used Piazza? Oh no, yeah, I guess not. Anyway, this is like this is basically a discussion board for the course. So let me hide this for a second while I go to web courses. Just want to enter the student view first. Okay, so this is what web courses looks like. The home page has all the links you need for the course. So the syllabus with lecture notes, all the project descriptions, and here's an invite for this Ed Discussions site. And if you go here, you'll be able to join and sign up on this site. So it's just basically a forum for asking questions. You can ask anonymously. If you don't want to reveal your name, you can send private messages to the instruction staff. And the benefit here is that rather than emailing me the same question 100 times, everyone will be able to see the answer if you so choose to make it public. So and then other instruction staff will be able to help you as well. So if I take a day or two to reply, a TA or a grader might be able to help you faster. So ask your questions here on this site, and also look there for answers to other questions, because somebody else might have asked your question already and then you already have the answer. Make sense? Yeah. Yeah, I mean you'll probably get a faster response. My email inbox has it's pretty bad. So certainly email me. I mean, especially if you have, you can ask private questions on here, but if you have something unrelated to the course, something related to SAS or some medical issue or something else, you can email me. Make a good subject and email me again if you don't hear back in like a day or two about the course. But yeah, this is a much better place for the course to ask questions, and you can ask questions anonymously and privately to instruction staff. Okay, and then GitHub we talked about. So there'll be links for all of the projects here. You just click on the link, and because you have a if you have a GitHub, most of you have a GitHub account already, it'll automatically create a repository in this COP-3402 organization. Yeah, so I already accepted the assignment before. And you'll see when we assign the projects and web courses, there'll be a link also here to do that. And so feel free to reach out on Ed Discussions if you have any issues getting your repository set up. The Simple C project will come soon. I'm waiting on GitHub Classrooms to change how they do assignments. So in the past, you would just get a template repository to start with, which I want to give you. But in this month, they're going to change it so that you fork a repository. We'll talk about that more next week. But it means that I can make changes. I can make fixes to the template that you can update. Anyway, we'll talk about that more next week. So yeah, kind of talked about web courses, talked about the course webpage, Ed Discussions. So in the past, somehow some students have made repositories on their personal GitHub account. I don't know how they accomplished that. But make sure you put it on the GitHub Classrooms organization, COP-3402. You shouldn't have your repository public for people to see. It's technically a violation. It's cheating because you're revealing your assignment to the world. Okay, so let's. So who would like to take a break? Should we take a break now? I think it's a good point to take a break. Who would not like to take a break? It seems ambivalent. All right, let's take a break. Let's take a break. Let's take a 10-minute break. Yeah, so we should have plenty of time. Should be able to leave early. So let's take a 10-minute break.
Like you go off of images and then you handwrite them.
All right, welcome back, everyone. Sorry for the delay. It was a little more than 10 minutes. All right, so let's continue with the lecture notes, the second half of this lecture. So it'll be pretty light today. All right, so I have a kind of an ulterior motive for the structure of this course. So I'm happy to hear some positive feedback about the structure of the course. So as I said, I really want you to actually get this project done, and I believe that failure is kind of a part of learning. And in a classroom setting, if you fail once and your grade is destroyed, you don't have this incentive to let yourself kind of fail and try again and learn again. So that's why I structure the project the way it is. But I have an ulterior motive for this project. So even if you could not care less about compilers and system software, one of the goals of this course is to make you a better programmer. We don't have automated programming yet. Who knows if we ever will. So we still have need for software developers. I think they still make a good amount of money. I haven't seen salaries recently, but having this programming skill is useful in general, being able to reason computationally. And so one of the goals of this course, kind of hidden goal for me, is to make you a better programmer. And in my opinion, people who are good programmers know really well these three things. They know their language. And so that's why it's so useful to be able to understand how the compiler works and how to see how this language is actually implemented. And so they know their language really well. They know the ins and outs. They know what's going to be fast. They know what's going to be slow. They know how to achieve a certain solution to a problem that's going to be efficient, easy to write, it's going to be easy to maintain, that's going to be easy to show that it's correct. Great programmers also know their programming environment. This is why I focus on using the command line. This command line is like one of the most powerful programming environments you have. You have so much flexibility in not just programming, but operating your machine, taking full power of what the operating system has to offer you. So they know their programming environment really well. Even if that's an IDE or some environment that you're using for development, understanding that programming well. And this might be a little controversial, they know some computational theory. They know some of the academic stuff. Because as we'll see when we're talking about solving the compiler problem, having some knowledge of discrete math helps when solving problems. Being able to frame problems in mathematical way, for instance, using set theoretic notations to frame solutions to problems can be much easier than trying to decompose everything into a complex series of loops. And if you ever, who's ever programmed in Python? You guys ever do Python? It's like everyone, is it the intro course here now? I think the intro courses now actually are in Python. And so Python and higher level languages actually have let you program in set theory, basically. They let you operate on sets if you ever use list comprehensions or set comprehensions. And so being able to have that kind of high level abstract reasoning about problem solving can help you, even if you're writing in assembly or C, being able to reason about your solution in this mathematical way can help you solve the problem either more efficiently, more correctly. Okay, so knowing the language, you can't program without it. Helps to understand what those language constructs actually mean. And the compiler is what is actually implementing those constructs. So if you understand how those constructs are implemented, for instance, you know that a for loop is implemented usually using branches at the assembly level and how that gets optimized away in certain cases, or when not to use a for loop, it's useful to understand how the compiler actually implements that construct. So the programming environment becomes much more critical when you're doing software maintenance or large-scale development, because there's all sorts of tooling out there to help you build, deploy, organize your software. And the compiler is a part of this programming environment. I mean, it's the part that implements the language, but there's a whole bunch of other pieces to the programming environment that actually get your idea and your code actually running on a physical machine. Computational theory, it gives you new mental models about programming. So even if you're programming in C and you think there's no abstract math going on here, there is a mental model for C. It's a very simple one. You have like RAM and processors. You have RAM and computation. You have pointers in C, but it's still a mental model of the machine. I mean, if you go down to the assembly level, the assembly and the machine don't really distinguish between pointer values and integers, which is why you have certain security vulnerabilities due to that conflation of the two. And it's a very simple mental model, but in computational theory, you get other kinds of mental model. Like, I know discrete is not required for this course, as I just discovered from people's questions. But if you learn about automata, like a finite state machine, that's one mental model of computation that it's not general purpose. It can't write any kind of program that's computable. But it's a very useful mental model that you can apply if you figure out which mental model is best for or which computational model is best for your problem. It'll make the problem solving easier because people have already worked out how that computational model can be implemented. And so compilers use several different computational models for achieving its job, what is a very difficult job of processing the input language, and uses these computational models to make that much, much easier. So much easier, in fact, that we don't even have to write part of the front end. We can use a tool that will generate the code for some phases of the compiler. And we'll get into that in a couple of weeks. So has anyone ever heard of the Perl programming language? Yeah, it's kind of been replaced largely by Python in the common use cases. But the developer of that language highlighted what he called three virtues of a great programmer. The first one may surprise you, it's laziness. Now this is not laziness as in, well, I'm just not going to do it. This is laziness in that, well, I want to do this, but I don't want to spend a lot of time doing this. So it's the quality that makes you go to great effort to reduce your overall expenditure. There's a funny XKCD comic about somebody spending 2 weeks to automate something that they could have done by hand, in a day. That's kind of the laziness we're talking about here. The idea that you work really hard to figure out a way to write a good quality program that will solve a problem for you. Maybe you don't actually need to go to that length, but when we're talking about a compiler, for instance, trying to be lazy about tackling these difficult parts of writing a compiler is a virtue. Impatience. So when I see a student, when I see their workflow and they have to click on several windows, they have to save, it takes them a few minutes just to recompile and run their program, that makes me feel impatient. I try to make my programming environment really fast where I can rapidly change and test my code. And I'll go over next week your programming environment that'll help you actually maybe be a little faster. There's a little learning curve in learning these tools, but if you can set up your workflow, you can be much faster. It can look like you're a much better program than you are. You make the programming job easier for yourself rather than trying to tackle a hard problem. You spend time trying to make the problem easier. And we'll talk about that more when we try to write this compiler. And hubris, basically bravery, that you can actually do this. That makes you actually want to write these challenging programs that if other people look at it, they'll say, yeah, this is a good program. So anyway, kind of tongue-in-cheek, but that laziness part I kind of do want to actually emphasize. And remember, it's not laziness like I'm not going to do it. It's you want to make the problem as easy for yourself as you possibly can. And this is actually where computational theory comes in as well, because you can make it much easier to frame the problem. Okay, so in order to kind of motivate my version of laziness in programming, let me ask you a question first. So what is a bug? I mean, in the programming context, what's a bug? Yeah. Okay, something that causes your code to not work right. All right, yeah.
An unexpected behavior in a program.
Okay, unexpected behavior in a program. Other views? Yeah.
I was going to say, kind of very similar to those. When your program does something you don't want to do.
Okay, your program, yeah, that's kind of like unexpected behavior, right? Program does something you don't want to do. Yeah, Joe. Oh, no, okay. So we have two kind of competing answers. The program does something it's not supposed to, right? And the program does something that is unexpected. So who's doing the expecting here? In the expectation? Who's doing the expectation? Yeah. The user, the programmer, is expecting the program to do something. So in my definition, a program is actually not the program does something wrong. So that's kind of like the view, that's the view you have when you're trying to like get the computer to do what it's supposed to do, and you say, this program is not working. But what's really going on is what your colleagues said, which is that the program is doing exactly what it's supposed to do. The machine is rarely incorrect. There are certain, there are cases, sunspots can cause the CPU, or if you're overloading, can cause the CPU to like not have the right instruction. But usually the electrical engineers are pretty good at making the hardware work correctly. And so a bug is not anything about the program being wrong. It's the expectation of what it's supposed to do. And so there's like a real reality check in programming when you have an idea of what the program is supposed to do and it's not working the way you want. And at least in my opinion, the computer is right. It's our minds that's wrong. And so we have evidence in front of us that shows that it's our thinking about the program that's wrong. And so sure, we wanted it to work in this specific way, but it's not. And so in order to do that, we need to actually understand what the program is doing. So one kind of exception to this, I said there's exceptions, is compiler bugs. And you guys are actually writing the compiler. And so if you wrote a program that does exactly what it's supposed to do in the meaning of that program, but the compiler has a bug, the compiler doesn't faithfully translate that program, then actually your programming environment is actually responsible for that. But usually when we're coding, these tool chains are usually pretty correct. Usually we're not finding compiler bugs, although there's research that actually finds compiler bugs. They are being fixed. But usually when we're coding, it's us that's wrong. It's us that's wrong. It's wrong about what the program is actually doing. So we can't wish the program to do, the machine to do what we want it to do. Okay, so here's a really simple 3-step process for debugging. And so in the thinking that a bug is, I don't know why the program is doing what it's doing. It's doing what it's supposed to do, most likely, but I don't understand why it's doing what it's doing. I have an idea in my head about what it's supposed to do, but the machine is not doing that. And so here's a 3-step process to debugging that you can employ every time the program is not doing what you think it's supposed to be doing. So the first step is not to start digging into your code. The first step is to take that buggy test case, because the reason you know that it's not doing what you think it's supposed to be doing,
is that you ran an input and it didn't give you the output you wanted, right? Now that could be a seg fault, but it could just be the output, gives you an output, but it's not the right output. So the first step is to narrow down the problem. This is the laziness part. Don't try to take this giant test case, especially in the compiler world where your test case might be a big program, like a 50-line program. Instead, before you even start debugging, pare that input down. Try to zero in on what part of the input is actually causing that incorrectness, that unexpected behavior. See what I'm saying? So try to narrow down the input program as much as you can to parts that you're pretty sure are working correctly. And now, we'll talk about how to actually build up your program so that you can have confidence that part of your compiler is working. But try to narrow down the test case as much as you can. And now, go to your code. Use that test case to tell you where in the code that problem is happening. Because with the compiler, you have this big input program, and each part of that input program is going through a different path of your compiler. You have lots of if branches, lots of functions in your code. There's lots of different paths that even one test case may be taking. And trying to figure out what path that is hard. And so if you can narrow down the input, and then use print statements, use a debugging tool. I can show you some debugging tools, but I usually just use print statements to try to figure out exactly where in the code that it's not doing what it's supposed to do. Because surely there's some path in the program where it's working correctly, and it's maybe halfway through your code that there's where the bug is happening. And then once you have an idea of where the problem might be happening, trace your code step by step to see what it really does. So disabuse yourself of what you hope it does, and actually look at the code and interpret in your head and use print statements or a debugging tool to help look at the variable values and actually step by step check, is this doing exactly what is this doing exactly, and where is it differing from what I think it should be doing? Does that kind of make sense? So it's really about disabusing yourself of what you hope or feel the code is doing, and at a laser focused level, looking at each step of your program and understanding what it's actually doing. And doing that, I've had students come to my office hours and they say, hey, this doesn't work. And they ask me, can you help? And I'm like, no, I can't, because debugging is really hard. And so I can't figure it out either if you have this big program with this complicated input. And so I just do this process with them. And oftentimes, I'll do the process with them. I won't see it, they'll see it. And they'll say, oh, yeah, here, I made this little mistake. And so this process of forcing you to look step by step in very fine-grained detail at your program, you'll just know, you'll notice your own mistake. Because you wrote the code, and you have a good sense, usually, of what the program is doing. But these bugs, are often little insignificant errors that if you were paying attention, or if you, review it carefully, you would not have made. So there's a three-step process for debugging your compiler. Questions on this? Now, I will say it's much less gratifying than just going into your code and being a genius and saying, oh, I noticed that bug right there and I fixed it. You can do that, you can try to do that, but I'm lazy, so I want to make it easier for myself to debug. I don't want to have to do that. Okay. So now that will work on a little piece of code. You can only narrow down the test case so much. So let me give you a little different way of thinking about coding, maybe a different way of thinking about coding that maybe you never thought of before. So usually in class, your goal is just get through the programming assignment, hack as much as you can until the test cases work or until it's good enough, right? I think I've done this, I think everyone does this. And that can work. If you're sufficiently smart, maybe you can do that for a 200-line program. But no matter how smart you are, there's always going to be a big enough program or a big enough problem where you cannot tackle it just by hacking away, and then running your inputs and having it be correct. I challenge anyone to show me someone who can do that. The Linux kernel, for instance, is 20 million lines of code. There's no person on earth who can do that for 20 million lines of code. So here's a little pithy kind of somewhat tongue-in-cheek statement from Brian Kernahan, one of the AT&T people who were working on the C toolchain. And he had this great quote that I love. Everyone knows that debugging is twice as hard as writing a program in the first place. Kind of agreed, right? Debugging is really hard. So if you're as clever as you can be when you write it, how will you ever debug it? So if you use all your cleverness to try to hack together this program as quickly as possible and use as many tricks as you can think of, and then something goes wrong in the program, I mean, now you got to debug that thing. So let me give you another view of coding that I hope will help with building this, large, complicated piece of software. So one way to think about this bug problem, to kind of put some polysyllabic words on this, is that we have the specification, that's what you think the program will do, what you want it to do, and we have the implementation, the actual code, and the machine that it runs on. And one way to think about the goal of coding, software development, is to make the implementation and the specification match. Make sense? And that's why a bug emerges, because you have a specification in mind, even if it's informal or it's, you never said it to anyone, but it's in your mind. And then you have the actual code. And so the goal of debugging and the goal of implementation in the first place is to make those two things match. And so in that frame, there is no such thing as a bug. There's just an implementation and a specification. And a bug is just another way of saying, well, my implementation doesn't match my specification. Okay, so the kind of intro CS student, which was me as well, way of trying to write a program is to take this specification, and this might be like what your CS1 professor told you to write. They said, hey, write this program that does this complicated sorting algorithm or something. And you as the programmer have to write some C program that's gonna make this specification work. So here's you, the programmer, with your laptop here, I guess. And your job is to turn specifications into code. Like the joke is that mathematicians turn coffee into theorems. You turn specifications into code. And so the classic way that students always approach this is they're like, all right, I'm gonna take this whole specification and I'm just gonna try to write the whole thing at once. I'm just gonna get it all written. And so you sit at your machine and you get some of the implementation right, you're coding and coding and coding, coding and coding and coding, and you may end up with like a little bug here, you're coding and coding and coding, then you get kind of tired, you want to go play video games, and you just leave the rest of your code unimplemented. And in my framing of this, does the specification match the implementation? That means that this entire section of the specification that you just stopped implementing is technically wrong, right? That whole specification is wrong, all the stuff that you haven't gotten to yet. So in your mind, you're thinking, well, I just didn't write it yet. But in the view of a bug, that means that this whole part of your specification that you just have not implemented yet is just wrong. It just won't work, right? With me? Make sense? Has anyone done this before? Just sit down and try to code it if you want to admit it. So I've done it, definitely done this. I mean, there's definitely value in hacking some of this, hacking code together. But for a complex, large project like a compiler, or what you'll probably have to do if you work for some tech company, it's not going to fly. You're not going to be able to hack this stuff out in one night of binge programming. Okay, so that's the traditional model, the student model of coding. So let me show you a different way to think about programming. So instead of doing what we did here, which was to effectively cut off part of the implementation, what we did here is we said, all right, I'm implementing the whole specification, but I'm just going to cut off this part of the implementation. I'm just not going to worry about it now. Instead, the lazy way and the easier way, is instead of cutting down the implementation you're trying to do, cut down the specification that you need to work on. So when I start a new programming project, I'll literally start with hello world. And so I'll make the solution that I'm trying to achieve is, well, can I write a hello world program? That's really easy, right? And so I've already made a program where the specification and implementation match. Okay, so let me show this visually, what this kind of looks like, to give you a rough sense, and then I'll give you some practical ways to actually do this in coding. So here's the lazy and easy way of doing this. So here's our specification and implementation again. Here's me, the lazy coder. Instead, before you even start coding, cut off a little piece of the specification that you know is going to be easy, that you can do correctly. And only like give yourself the challenge of implementing that one little piece. I'll literally say, okay, hello world, I need a program that will run and print something out. And then when you go to implement, only implement as much as you need in order to get that piece of the specification implemented. Make sense? So now this isn't going to save you from writing bugs. I mean, it's going to happen. So maybe the next time you go to implement another piece of what the program is supposed to do, you have a little bug here. But before moving on, you test your code as you go along. Before you move on to the next piece of the specification, you test your code, and you test as you go along. You try to make thorough test cases that test each piece of your implementation. It feels much slower to do this because you're sort of going at a much kind of slow pace. It's basically the tortoise versus the hare. That hare approach, where you're trying to program everything at once, is going to lead to lots and lots of bugs, lots and lots of times where the implementation doesn't match specification. But when using this slow, methodical process, you know exactly where your bug's going to be, or at least you know much more precisely where your bug's going to be. And so instead of, before you move on, you go to this little piece and you solve that bug. And it's already narrowed down for you because you haven't even bothered trying to write a lot of the other program or trying to implement a lot of the specification of the program. Kind of make sense? Okay, cool. Does anyone actually use this approach right now? A few people? Who's never used this approach? Abstractly, okay. But maybe you don't know if you use this approach. I mean, if you only write small programs, there's nothing really to break down. Okay, and so the idea is that even if you leave that bug in there, by having this clear idea of the specification, that you'll know that you'll have a better idea of where in that implementation your bug is appearing. Okay, so that's my lazy way of doing this. And it's really kind of delayed gratification. You take the time to organize your code in such a way that you narrow down the problem. And it takes extra time to do this, for sure. So if you're writing a really small program, hacking it together may actually be worthwhile. But if you're writing something that is prone to be buggy, that's really tricky and challenging, like writing a compiler, doing this process of breaking down the problem will save you time in the long run. It'll save you debugging time. So it's basically divide and conquer. Break the problem down into smaller parts. And now doing this is not easy. But I'd rather spend my time trying to figure out a way to make the programming easy and breaking down the problem in such a way that'll make the coding easy and reduce my debugging time. So yeah, finishing the code feels good to do it fast, but debugging really sucks. So take the time, start the projects early, take the time to do it, and remember that if you fail and you don't get it in on time or you don't get everything solved, you have the rest of the semester to improve the situation. So it takes you a longer time to do it. So, just to beat a dead horse, spend time now, save debugging time later. Doing this process of breaking down the specification, it takes time, it takes experience, it takes making mistakes, like maybe you didn't break the problem down in the right way, or you were trying to generalize too much and made it hard for yourself. You'll learn about this in like OOP, like Principles of Object-Oriented Programming. Object orientation feels useless when you're writing small programs, but when you're doing large programs, it just gives you mechanisms for breaking the problem down. Yeah, so premature generalizations, root of all evil, don't try to generalize too early. Instead, refactor. So if you notice that you didn't have a good design of your code, you didn't break it down the right way, don't rewrite from scratch. Don't try to suffer with your difficult or cumbersome generalization. Refactor the code. So don't be afraid to go back to your code and look at it. So if you've ever had the experience of, I don't ever want to look at this piece of code again, which I have as well, then you may want to, you're probably just hacking away, and you don't want to have to deal with debugging it again. So don't be afraid to look at your code again. Put comments, write functions carefully. Don't be afraid to refactor your code, which means reorganizing it without changing the behavior. So if you notice that you have the same piece of code that's duplicated everywhere and you wrote it the second or third time, don't be afraid to go back, refactor it, pull out that code into a separate function, test it, make sure it works, and then proceed with your coding. Don't be afraid to refactor, to reorganize your code after the fact. All right, questions? Now even if this is all abstract, even if you're not listening to me now, you'll encounter this in this class. You're gonna have hard bugs to solve, and you're very much on your own. That's what's hard and also fun about programming is it's all on you. You get all the credit, you get all the pain of coding. And so that bug is your coding, it's your mistake, it's my mistake. And so using this methodical, careful approach to avoid the desire to go ahead and have a complete program will make it faster, I promise you, in the long run. You'll code this faster if you code slower. Okay, so how do we actually do this? The programming language design world has made programming tools that will help you organize your code. And these are called abstractions. So if you've ever wondered why you need to program in C and you can't just why not just program in assembly? The point is that the programming language gives you abstractions that make it easier to organize your code. There's no computational power difference between a C program and an assembly program. Anything you can do in C in terms of computational power is the same as what you can do in assembly. It's the same as what you can do in some high-level functional language in Scala or Python. They're all computationally equivalent in terms of what numbers you can compute. The difference is what language constructs you have available to you to make your programming life easier. So abstractions, they hide unnecessary details. They're physical examples of this. So if you've ever had to recharge your laptop, there's no difference between splicing the wires and soldering it or joining it with the electrical system in the building. You can just take the raw wires, hopefully turn off the electricity, twist them together, and you'll power your laptop, right? So there's no difference in the power you get from using a plug, using an outlet. But they're different to use, right? There's extra material and extra work in designing that interface. And they don't provide you extra functionality in terms of electric power. But it's much, much easier to know that you have a socket available and you can plug into any socket without having to pull out the wires, figure out positive and negative, twist them together. See what I'm saying? Same thing with a lock. So there's lots of implementations of locks. There's wafer locks, tumbler locks, electromagnetic locks, but they all have the same interface. You have a key and you have a lock. And the usage of it might vary slightly, but that abstraction is the same for all locks. And now there is no way that I know of saying what's the right abstraction, what's the right interface. So an electric socket, there are certain devices that require higher voltage, and you have to get a special line to your house, and so you can't use that socket. And so it might not be the best socket for every possible case, but these interface decisions, they're based on what the use of that abstraction is going to be. So there's no way to sit down that I know of and write all your functions ahead of time and say, well, these are all the functions I'm going to need, without thinking about who's going to use them, how they're going to be used. Okay, anyway, so the most basic abstraction that basically all languages give you is the function abstraction. And you're probably so used to it now that you don't even think of it as an abstraction. But once we actually see how functions are implemented in assembly on a machine, the machine has no notion. The machine has no instruction that says, here, this is a function. There's a call instruction, but it doesn't do what you think it does. The function abstraction is, it just basically gives you a name for a snippet of code. It gives you some encapsulation, gives you local variables, and it saves the state of that function so that you can call things recursively. And we'll look at how that actually works once we get to the back end of the compiler. And you'll actually implement this and see how the function abstraction actually works under the hood. You probably are so used to using it that you don't even think of it as an abstraction. You think of it as just like what the machine gives you. But the processor doesn't actually give you support for C-like functions. So abstractly, this is kind of software engineering. When we break down the specification, we use these abstractions to map to these particular parts of the specification. In the compiler, it'll be like front end and back end, and we'll see all the faces of it. And the idea is that you can encapsulate pieces of your specification in these abstractions. You can test them individually. You don't have to test them when running the whole program. You can actually write tests that just test a function. And as long as you've thoroughly tested that component, you don't have to worry about it anymore. So when you're going to do debugging, if you've thoroughly tested that function you wrote, that piece of the compiler, that piece of your program, you can put it as low priority for debugging. So if you get a bug, you can say, well, I tested that component thoroughly. I'm not going to start there in my debugging. I'm going to start with this new component that I'm currently implementing. And so this is why that methodical way of implementing the specification a piece at a time is so useful for making quality, large software that's easy to debug. Because you make sure that component is as sound as you can get it. And then when you go on to other components of your system, you probably don't have to worry about that component. As long as it's well-defined, it's used correctly, you probably don't have to worry about it. And this is how large systems are composed. In past courses, I've shown the layers of like the Linux operating system. And even inside of that 20 million chunk of code, all those system calls they give you, like opening files, reading and writing files, there are several layers of abstraction beneath that go from the hardware, like say SSD, hard drive, flash drives, to an abstract notion of a drive, to an abstract notion of file systems, and then finally up to like files and paths that you use. Those files and paths are nowhere physically, that notion of a file and path does not physically exist. The hard drive just has like blocks that you can make 0 and 1. It's the operating system that creates this abstraction, this kind of deception that you have files and folders, but it's really just a flat set of binary data, effectively. Okay. So questions? I know this is a little abstract and distant, but as we go and build our compiler, we'll see more about this, how we actually break the compiler down. And so just to wrap up bugs are almost never, at least for this class, going to be due to the program doing something wrong. It's that our expectation about what the program is supposed to do does not match. Our specification does not match our implementation. Break down the specification, not the implementation. Break down the specification first. Implement each piece, because it's got to be way easier to do that. Test it thoroughly, so that way you don't have to test the whole specification. And then build the program up by combining these abstractions. Now that part is tricky, but I'd much rather be doing that than sitting debugging, 10,000 line programs. So there's an interesting paper that you might want to read if you're interested in this approach. It's a very short and simple paper. It goes through this one approach of developing abstractions to create a program, to create a solution to a problem. That's a tricky problem. 8 queens problem, I guess maybe in CS1. Who's heard of the 8 queens problem? Oh, so some of you. Okay, so 8 queen problem, it's how do you put 8 queens on a board where none of them can attack each other. Tricky to do by hand, but you can write a program to do it. But the idea is this is not the 8 queens problem, but to show how to go from a high-level abstraction, which just says, here's a board, give me the 8 queens and their positions. And it shows how to break the problem down little by little into gradually smaller and smaller abstractions. So you can break that down into, well, whatever they do here. You can read the paper, but it's basically a tree of abstractions. And at the bottom, you can finally implement the individual pieces. And it just shows it's one classic way. You can see it's from like 50 years ago at this point. Nicholas Worth, he's a kind of compiler, writer, and designer and instructor, teacher. You can see one example of actually using this, breaking down the specification approach to do implementation. And there'll be a link in the notes, so all this is in the notes. Okay, so for the last part of this class, I'd like to go over setting up the programming environment for this course. All right, so who's used virtual machines before? Oh, a lot of people. Where did you use virtual machines? Was it for class? No, you just used them? What's that? Intro to C, okay. So you've used virtual machines before. So I use this really for grading to kind of make sure everybody has the same programming environment, has the same, because we're actually going to be compiling to, Intel assembly. So I want to make sure everyone's hardware is the same. The virtual machine it's an emulator. Anyone ever used video game emulators? Aha, caught you. No, I'm just kidding. So video game emulators, they're good for preserving history. There's a whole site on archive.org where you can actually play emulated games, I think legally. They're a library of games. So an emulator is just a piece of software that pretends to be a specific piece of hardware. The hardware is like the interpreter of the machine code. And so the machine code doesn't know whether it's on hardware or software. And in fact, Intel processors are really running a type of software called microcode that implements the instructions. But that's all a virtual machine is. It's an emulator for a particular piece of hardware. So just some terminology. The host operating system, this is the operating system that's running on your machine. So if you're running a Windows machine, if you've installed Windows on your laptop, Windows is the host operating system. The guest operating system is the one running in the virtual machine. Make sense? So for those who are on Windows, I'm going to give you a Linux virtual machine and some tooling to install it. And so the guest operating system will be that Linux, it'll be Ubuntu. That Linux operating system, the host will be Windows. Hypervisor is the tool that actually manages between these two. We don't have to talk about it. This isn't an OS course. So there's two pieces of software that you'll need to install in order to use the virtualization environment that I've set up for you. So one is VirtualBox. Has anyone used VirtualBox? Who's used VirtualBox? Not many, or a little less than half. So install this. It's free and open source software. And there's another tool, Vagrant. Who's used Vagrant before? Not many. I didn't think many. Who's used Docker? Okay, more. So Vagrant is kind of like Docker. It's basically a command line tool for managing virtual machines. So download and install these two pieces of software. If you have issues, go on Ed Discussions. I have some tips for Windows users. And so I have this configuration file that you can use with Vagrant to set up the virtual machine. Oops. Yeah.
Will you download the AMD64 or the i6-86?
I think probably for your machine it's the AMD64. So if you're on a 32-bit Intel machine, I don't know what happens with like the ARM-based Macs. I hope VirtualBox works on them. Let me know if it doesn't. I've not tried that. But yeah, if you're using a 64-bit Intel processor, it's got to be the AMD 64 because AMD beat Intel to the punch when developing a 64-bit ISA, and that's the one that got standardized, de facto standardization. Okay, so you'll need to download that Vagrant file. Go to your command line shell. If you're in Windows, this is your Windows shell, not the Windows, not WSL, not the Windows system for Linux. And then in the folder where you have the Vagrant file, run Vagrant up. So let me actually just show these on the command line. Well, let me give these guys first, and then I'll do a demo of actually installing this virtual machine. So you might get an error message when firing the virtual machine that says you need VTX support or SVM support, you need hardware support. So yeah, the processors have support that like makes virtualization faster basically. And it might be a BIOS setting for setting this up. So if you have issues or if you have a machine that's like 10 years old, you may not have it at all, come talk to me if you have any issues. Who uses WSL? Who uses WSL? So this won't work properly, I don't think, in WSL, so use the Windows command prompt. And then once you fire up Vagrant, you'll have a Linux, you'll be in your guest operating system. I think there's also been cases where the antivirus software was basically doing a man-in-the-middle attack on your secure web traffic, and Vagrant is detecting this. You know, they may be trying to help you, but they are using a security vulnerability in order to apparently help you. You know, prevent you from, I don't know what it's doing, but I've seen that in the past. Okay, so let me do a live demo, and I'll go through all the instructions in the demo. I already have this folder. Let me destroy everything. So destroy. Oops. So destroy is if you want to start fresh. Make sure you don't have anything important in your virtual machine. Okay, so the first thing to do is to get this file. So I have a file already in here, Vagrant file. So download that, put it in some folder where you want to house your virtual machine and maybe your project. And once you have that Vagrant file here in your folder, can anyone not read this or not see this? Okay. Once you have your Vagrant file, all you got to do is run Vagrant up in the same directory that houses the Vagrant file. This will download and configure an Ubuntu, a virtual machine that has Ubuntu already installed on it. Ubuntu is a Linux-based operating system. So the machine is booting up. It'll take a little while to download. Uh-oh. Okay. So it'll also, I'll go over this here on step 6. So inside it, while this is installing, inside of here, there's also a what they call a provision script. So this is installing all of the libraries that you're going to need for your project. So this is also why it's useful to use this virtual machine. You won't have like, hey, I don't have this tool, or your command doesn't work. This just standardizes everybody's setup so that when I give instructions and I give commands, they can be exact, and they should work exactly as given. Internet connection is a little slow. So it will take a little while to download and configure the virtual machine. And so maybe I shouldn't have destroyed it. I should have just kept it there. But now you can see in real time how long it'll take. So it's just running this update command here. This is the package manager for Debian and Ubuntu-based Linux machines. And this is how you install packages. And to kill time, this is tooling for building C programs. Oh yeah, question? Say again? You don't have to write the code in the virtual machine. So, and I'll get to this on step 6, but the Vagrant setup will automatically sync a folder between your host OS and your guest OS. So you could actually do all your development there in the synced folder, but you should be building and running in your virtual machine. Yeah? No particular reason. Vagrant's, I don't know, no particular reason. Vagrant, I just got used to using Vagrant. And it gives me complete command line control. I guess Docker does as well, but It's just easy. It's easy to use. You can literally just say vagrant init and then the name of the OS you want, and then just say vagrant up, vagrant SSH, and voila, you've got a command line virtual machine. It was really the command line support, I guess. I think Docker probably can do it, but yeah.
If we're building a virtual machine on Ubuntu, is all configurations the same?
If you're building the virtual machine on Ubuntu,
Yeah, like if your computer already has Ubuntu.
I would still use the virtual machine because there may be differences in your hardware, there may be differences in, yeah. I mean, you could try just setting everything up in your own Ubuntu distribution. We're gonna be grading in the virtual machine. There may be slight differences between the versions. So if you'd like to go for it, if you'd like to try. But the virtual machine is like the officially supported development environment. But yeah, if you already have this version of it, I mean, the tooling might be a little different. You know, Bison and Flex, the tools that we use for generative compiler, they do have slight differences between versions. Also, I'm going to be giving you a precompiled binary for the phases of the compiler that you're not working on. Like when you're working on phase 3 of the compiler, I give you phase 1 and 2. And to make sure there's binary compatibility, the virtual machine will pretty much guarantee that. If you're on your own machine, probably it'll work. It might work, but it might not. So I would just use the virtual machine, even if you're on Linux. So I'm on Linux here. I'm on an Ubuntu machine. But I still use a virtual machine for the class, just to make sure that everyone has the exact same machine. This is unfortunately taking a long time, longer than I hoped. Make is these are the build tools. These are the tools for actually compiling and building C. Git is the version control software. We'll go over that next time, how to actually use that. Bison and Flex are compiler generators. They're tools that will help generate the front end of the compiler. Nano, Emacs, and Vim are sort of the big 3 editors if you want to do editing in the virtual machine on the command line, which I recommend, although there is a learning curve. And then HTOP is for looking at processes, and Keychain is for managing your SSH keys. So if you want to make it easy to push and pull from GitHub, have you ever used GitHub? Who's used GitHub? And when you say git push, do you type in your username and password every time? Or you use the SSH keys? Who's that? Okay, great. Okay, that's good. So it's now installing stuff. All right, so while this is going, I'll go over commands to run. So vagrant up will create your machine. Vagrant SSH will SSH into it, and then as you'll see, you'll get it'll look like you're still on the command line, but you'll see a different prompt. And this is why I like vagrant, because you can just very easily, it's as if you're remoting in to Eustace or remoting into a machine. Inside the guest machine, /vagrant, root folder /vagrant, is synced to the folder where you ran vagrant, where you have your vagrant file. So if you look on, in my folder here, I've got the solution, and I've got the compilers here, my compiler projects. So if you want to be able to work on your host OS, you have an IDE you like in Windows, you can work on it in this folder, whatever folder you fired up the virtual machine from. And then when you go to compile and run and even submit it with Git, you can do that within the virtual machine on the command line. If this ever finishes building, I'll be able to show you that. You just change directory to this /vagrant in the guest machine, in the guest OS, CD vagrant machine, vagrant. And you'll be in a folder that is synced with your host OS. To leave, you can type exit or Control-D on an empty command line. Questions so far on this? So pretty straightforward. If you want to, so that's how you can exit the virtual machine, Control-D or exit. If you want to like save battery life, or you want to halt the machine for any reason, inside of the guest OS, you can run this command, sudo shutdown -h now. It just says run as the administrator of the machine. Shutdown -h means halt, and now means you can shut down. You can set it to shut down in the future. Like this is what sysadmin use, but you just want it to shut down now. If you're in your host OS, you're in the folder, not in your virtual machine, you can say vagrant halt to just force the machine to shut down. Yeah?
So speaking of pseudo commands, what
Does Vagrant come with a default like passwords or anything for the
The virtual machine will have no password. Yeah, the virtual machine will have no passwords. I can show this. I can show this here. So now the machine is done. I just run Vagrant SSH. Oh, you can't see that. That's unfortunate alignment. Let me make this easier to see. Okay, so I ran Vagrant up. Once that's done, it'll take a while. Run Vagrant SSH. And now, that is very annoying alignment. All right, so now I'm in my virtual machine. One way to tell that you're in the virtual machine and not your host machine is the folder. Oh, yeah. I'll just make this very hot. Is the prompt will tell you you're the Vagrant user at the machine name. And these machines are already set up with like passwordless sudo. Sudo is how you run as administrator. I don't want to shut this down, but yeah, you don't need a password to run sudo. Sudo is the super user, the administrative user, if you're on Windows. Okay, so now I'm in my virtual machine, and if I change directory to Vagrant/Vagrant, you'll see that these files are the same as the ones in my host machine. So you can tell I'm on my host machine here because it says Paul at device, or you'll be in a Windows prompt. If you're on Windows, and you can just tell by looking at the prompts which machine you're in. It's just like when you SSH to Eustace, where you go into a remote machine. But it's all done with the command line. And you can see that these folders are the same, so if I touch a file on my host machine, so there's the file on my host machine, you'll see that it's on my guest machine as well. So here it is on my guest machine. Questions on this? So it takes a little bit to download these two programs and set up, initialize your virtual machine. But once you're there, you now have the same environment that everyone else in the class, all the graders, me, has. And if you're on Windows, you've got a fully functioning Linux OS. So you can halt the machine with sudo shutdown-h now. That's if you're in your guest machine. If you're in your host machine, so this is my host machine, you can see Paul at device, you run Vagrant halt, and it'll force the machine to shut down. Just like if you were in VirtualBox and you just went to like option power shutdown. This probably won't be necessary, but if I update that Vagrant file and you have to re-download it, you can run Vagrant provision. That will rerun. That'll rerun all this stuff here, this provision script. But probably won't have to do that. So I went over some of the gotchas. These are make sure your machine has virtualization support. You'll get an error message that's something like requires VTX or SVM, which is virtualization support on AMD, Intel and AMD hardware, respectively. In Windows, be sure you're not running Vagrant in WSL. And I've had, one of the reasons I do this is because I've had students in the past who are using WSL for their development, and there are like differences in either the binary format, there are differences in the tooling that's being used. I even had one weird case where they were getting a seg fault and it was being reported on a line that like was not the real line. There was some weird stuff going on. So that's why I just have everyone standardize this development environment. It takes a little bit to set up, but it's something you can do while like watching TV. I mean, it's not hard, you're just mostly waiting for stuff to happen. And if you have any questions or any issues at all, if we haven't covered everything, then go on Ed Discussions, make a new thread, ask questions. Other students have probably encountered your problem before. Yeah, and just watch out for antivirus and WSL. So if something goes really wrong and you need to like redo this whole thing, Vagrant destroy, as I showed at the beginning, but make sure you don't have anything saved in your virtual machine because you will lose your data. Do everything in that /Vagrant folder. Yeah?
Question, when we download the Taurus Vagrant file, can we download it as a text
Yeah, it's a text file. It should be fine. Yeah, yeah. All right, questions on Vagrant? Questions on the virtual machine? Okay, so the first assignment is available. I guess, I didn't make the virtual machine one available yet. But I will make that available now. You'll see, so make sure you do this GitHub username for academic activity, particularly if you're on financial aid. There'll be an assignment that asks you to do your virtual machine setup. You just have to answer yes, that you've set everything up. That's the assignment, you just say yes. And you can't lie, right? Academic integrity, so you can't lie. You actually have to set it up. So just make sure you set up your virtual machine. It'll make life easier. That's all you have to do this week. Sit down, have some tea or coffee, watch TV, set up your virtual machine. Let us know in the assignment when you've set it up. Otherwise, yeah, that's all the content I have for today. So we're done very early, so I'll stick around for questions. And have a good day, everyone.